Dear students, today we are going to find the expression for electric potential at any point due to an electric dipole. Now, before we really talk about the electric potential at any point, we will talk about two separate cases and then finally find this expression for electric potential at any point due to an electric dipole. Now, since it is not so very tough, therefore we are clubbing these two things together, so you need to be in alert mind. So here we are talking about, we are having an electric dipole whose dipole moment is P. It is having individual charge minus q and plus q. Its center lies at the origin of the coordinate system, and its length is taken to be, half length is taken to be equal to a small l. So here you see this is small l, this much distance. And now we have to find the electric potential at any point. We want to generalize the case, but before we really do it, we will find the electric potential due to an electric dipole at an axial point, means any point which lies on the extended part of the axis, or at an equatorial point, means any point that lies on the equator, means the divider line perpendicular bisector of the dipole. That any point lies on the equatorial line, that is perpendicular bisector line of the electric dipole. So let us say, consider we have to find the electric potential at any point P whose coordinate is x and y, but we are not going to talk about it right now. At first hand, we will find the electric potential due to an electric dipole at any point n, say for example, which lies on the axis of the dipole. Now here you see, if this point n lies at x distance from the center of the dipole, the distance of point A from n will be L plus x. You see this is L length, half length of the dipole, and the x is the distance from the center of the dipole from that point. So the total distance of A from n will be L plus x. And then we have to also we want to discuss that what is the distance of point B, means what is the distance of plus q charge from n. You see it is x minus l, because this distance l need to be subtracted from the total distance x. So that way the distance of point B and point A is from point n, which is lying on the equatorial point of the dipole. We have to find the electric potential. Now electric potential will be that due to minus q charge at point n, and that due to plus q charge at point n. So here we have done exactly the same thing. Electric potential due to minus q charge plus electric potential due to plus q charge at this point n will be given by kq by distance kq by r. We know the electric potential is given by the relation kq by r. We have already defined it. So here we are doing a minus kq by x plus l. The distance of A is x plus l from n. So we are having this expression. Minus sign is because of the minus charge present here, and electric potential at n due to plus q charge will be kq, positive sign because charge is positive, divided by distance is x minus l. So when we put them together, k and q are taken outside, it is common, and we are left with what? We are left with 1 by x minus l, this is positive, and minus 1 by x plus l. So on taking the LCM we have and solving it, we have kq2l, because x and here minus x both cancel each other, So here we are left with L, and minus minus becomes plus L, so it becomes 2L. So KQ2L divided by x square minus L square, because you see x minus L into x plus L becomes x square minus L square. So that this Q2L can be written as electric dipole moment, expression for electric dipole moment Q2L. So we write Kp by x square minus L square. This is the electric potential at an axial point due to an electric dipole. So but when we talk about any equatorial point, what happens? Plus Q charge is at same distance from that point M as is the plus Q charge from the point M. Means distance of minus Q charge from M and distance of plus Q charge from M will be equal, and therefore we can very well understand that potential due to minus Q plus potential due to plus Q at an equatorial point will be K minus KQ by distance, let us call it L square plus Y square. So under root L square plus Y square under root, this is the distance of M from A, and similarly we have KQ divided by under root L square plus Y square. Now what you see, that minus KQ by L square plus Y square whole under root plus KQ under root L square plus Y square whole under root. Therefore these two together becomes 0. That means for equatorial point the electric potential due to an electric dipole is always 0. So these are the two things you have to remember. Now we have found that what is the electric potential due to an electric dipole at an axial point and at an equatorial point. Now we want to find the electric potential due to an electric dipole at any point P. Now for simplifying the case, if we have x is much greater than L, then we ignore the L here, and so we are left with the expression for electric potential due to an electric dipole at far axial point is equal to Kp by x square, because L square is ignored as compared to x square. So this is the electric potential at far axial point due to an electric dipole. I believe that it is quite clear to you now. So when we want to find electric potential at any point due to an electric dipole, which is of course lying at a large distance as compared to the length of the dipole, and usually this is always true, because you see dipole we have defined is dipole is defined as the 2 point charges, large point charges separated by minimal distance. So if this distance is already minimal, it is very negligible, then in general that point will be always much bigger than the distance of that point will be much bigger than the half of the length of the dipole. So that way this situation in general exists and always remains true in general for all practical reasons. So now what we do is we are taking the component of electric dipole moment P, which for P cos theta, for which point P becomes axial, and if that becomes axial we can directly quote this relation for that axial position. We have electric potential for P cos theta, electric potential at point P will be Kp cos theta, that is the component of P cos theta is the component of P electric dipole moment, and that divided by distance square, that is whatever is the distance of P from the center of the electric dipole. And of course for the component P sin theta, that point becomes equatorial point, and for equatorial point we have electric potential always 0, and therefore total electric potential at point P will be that due to P component P cos theta only. means only p cos theta will contribute. So kp cos theta by r square, where what is r? R is the distance of that point from O if it is having the coordinate x and y. Therefore, where r square can be very much clearly seen is equal to x square plus y square. So you can even write it in terms of x square plus y square if it is two-dimensional case. That's all for today. Thank you.